Okay, this is Mr. Long, and we are going to talk about gas laws today. So, gas laws, they're based on the kinetic molecular theory. Now, I'm going to go through this, and it's going to be kind of fast, so you're going to need to pause me and then take notes, pause me again, or rewind, because I've already written all this down, so you're going to have to pause me a lot. Anyway, the kinetic molecular theory is based on the idea that particles of matter are always in motion. Gas particles are always in motion, of course. An ideal gas, as our book says, is an imaginary gas that perfectly fits all the assumptions of the kinetic molecular theory. And I'm going to go to a certain page of the book. We are in chapters 10 and 11 in our book. So I'm going to go to that part in chapter 10 where it talks about the kinetic molecular theory. Okay, I did not write this down, but I'm going to read the topic sentences from the kinetic molecular theory of gases on page 303 in our modern chemistry book. So, postulate number 1, gases consist of large numbers of tiny particles that are far apart relative to their size. Postulate number 2, collisions between gas particles and between particles and container walls are elastic. They are elastic collisions. And an elastic collision is one in which there is no net loss of kinetic energy. And yes, I do want you to write these down. Postulate number 3. Gas particles are in constant, rapid, random motion. They therefore possess kinetic energy, which is energy of motion. Number 4. There are no forces of attraction or repulsion between gas particles. And number 5. The average kinetic energy of gas particles depends on the temperature of the gas. And I have written down the equation for kinetic energy. And let's do this. Okay, the equation is KE is equal to 1/2 mv squared. So kinetic energy equals 1/2 mass times speed squared. Now STP is standard temperature and pressure, or 0 degrees Celsius and 1 atmosphere. Now there are other pressure units which we're going to get to in just a second. And characteristics of gases. Number 1, they can expand. They have expandability. Number 2, they are fluid. They have fluidity. Gas particles flow past each other, so they are considered to be fluids. They have low density. They have compressibility. You can put some gases in a container and you can make the walls and floor smaller, and therefore the pressure will increase. And they diffuse. There is diffusion, the random mixing of particles by motion. Now, one word that you don't know probably is called effusion. And this is where gas particles are under pressure and they pass through a tiny opening. For example, in our labs that we have, you have the gas spigots, and when you're going to hook up the Bunsen burner to it, you can turn on that gas and hear that gas go psss. So it comes out with a greater force, and there's a small little opening there. That's an example of effusion. And real gases. A real gas does not completely behave according to the kinetic molecular theory. I believe most gases are real gases. Okay, I hope you've been pausing me so you can write this down. page 2. We have a few units here, or words, terms. We have pressure, force per unit area on a surface. Barometer, it measures the atmospheric pressure, which you hear on your nightly weather man when he's given the weather. And the first scientist to invent the barometer was an Italian named Torricelli. This is Icelli, Torricelli. He invented the first barometer. Now, pressure units. We have several pressure units. So we have 760 millimeters of mercury, and these are all considered to be standard pressure. So we have 760 millimeters of mercury. That's equal to 760 torr. That's equal to 1 atmospheres, which is equal to 101.3 kPa or kilopascals. That's actually 0.325, but I think 0.3 will do. And when we are using these in our problems, the book here pretty much uses these as infinite sig figs, sort of like moles A and moles B from the coefficients in a balanced equation. Anyway, kPa is kilopascals, that's a metric unit. Now, our first problem on converting pressure units. Say we start with 0.830 atmospheres, and we want to convert that to millimeters of mercury and kPa, kilopascals. So just like in stoichiometry, in dimensional analysis, you start with what you're given. You draw your lines, and whatever unit this is, it has to be in the bottom of this first step. So here we're saying 1 atmosphere is equal to 760 millimeters of mercury. So we're converting from atmospheres to millimeters of mercury. Pull your numbers over, cancel out your units, you get 631 millimeters of mercury. And we get those 3 sig figs from this right here. Okay, and the other one that we're going to convert to kilopascals, it's the same starting point. This many atmospheres, and 1 atmosphere equals this many kilopascals. Cancel out the units, pull your numbers over, you get 84.1 kPa. Conversion within pressure units. Okay, let's go to page 3 now. All right, the first gas law is Boyle's law. Okay, this is when the volume of a fixed gas varies inversely with the pressure at constant temperature. What is inversely? Well, when one goes up, the other goes down. So this is inversely. One goes up, the other goes down. And as compared to directly, where they both go up, they both go down. Both go up, both go down. Now the graph of Boyle's law, which you need to know, you need to be able to recognize it and maybe even draw it. You got temperature is constant. So anyway, the volume of this gas varies inversely with the pressure. Volume and pressure and temperature is constant. So it's not going to be in the equation. So anyway, our equation for Boyle's law is P1V1 equals P2V2. Now here's an example. Example problem, a sample of O2 gas has a volume of 150 milliliters when its pressure is 0.947 atmospheres. What will the volume of the gas be at a pressure of 0.987 atmospheres if the temperature remains constant? Well, the way I want you to solve these, okay, I want you to pull out your information, just like in density problems. We've got 3 variables, volume, temperature, and pressure. Keep them in this order, please. So we'll have the first here and the second here. So first volume, second volume, first pressure, second pressure. So we look at this. The first volume is 150 milliliters. First pressure is 0.947 atmospheres. The second pressure is this. And if this remains constant, so you put a 2 dashes here, if the temperature is constant, what is the second volume? That's the question mark. This is the first step in solving your problem. The second step is writing your equation down. And I should have spaced this out more, but I thought I could fit it in on the end and didn't quite have enough room. So you write your equation for Boyle's law. Now you're going to plug it in. Pressure 1 goes there. Volume 1 is right there, so it goes there. That's a point. And then pressure 2 is right here. And then volume 2 is the unknown, and it goes there. So you plug it in. This is step 3, plugging it in. And now you're going to solve. So you got to isolate your unknown. So you're going to divide each side by 0.987, and that cancels 0.987. You do the math. V2 is equal to 144 milliliters of oxygen. So I want you to run through that with your calculator and see how that works out. Okay, but there you go. Now let's go to flip through page 4. And here is another problem. And this is on page 315 in your book. So you can flip to page 315. And this question is: a balloon filled with a helium gas has a volume of 500 milliliters at a pressure of 1 atmosphere. The balloon is released and reaches an altitude of 6.5 kilometers where the pressure is 0.5 atmospheres. Assuming that the temperature has remained the same, what volume does the gas occupy at this height? Well, step 1. Pull out your information: volume, temperature, and pressure. So our initial volume was 500 milliliters. Our initial pressure is 1 atmosphere. So this has infinite sig figs here. What's the second pressure? When the second volume, when the pressure decreases by half to 0.5 atmospheres. Temperature is constant, so that gets the dash. So this will be points here for pulling out your info. This one, P1 V1 equals P2 V2. That's the equation for Boyle's law. That gets your points. We're going to plug it in now. So P1, 1 atmosphere. V1 is 500 mils. And what we do is equal to P2, 0.5 atmospheres, times V2, our unknown. So we want to isolate the unknown, so divide each side by what is by your unknown. So divide each side by 0.5 atmospheres. This cancels. These units cancel right there. Do the math in your calculator, and you get V2 equals 500 divided by 0.5, which is equal to 1,000 milliliters. And the gas is helium. Okay, and you see that on the significant figures, the book has 0.5 atmospheres, which is 1 sig fig, 500 milliliters, which is also 1 sig fig. So we got 1 sig fig in the answer. The only time that this gets screwy with significant figures is when you're involved with temperature. Okay, so Charles's law, I'm going to stop it here, then I'll start again with Charles's law so I don't make these too long. I'll be right back.